So welcome to our Sunday, our second review session in thermodynamics. And what I've done is just prepared some sample questions that were emailed to me as of about maybe noon today. I was able to put in some additional problems. So what I'd like to do is kind of go through what I would say a variety of problems that I noticed were most missed from examining quiz results, as well as what was emailed. And the first one I wanted to say really is just the bread and butter equation of this entire chapter. We're asked to calculate delta G, Gibbs free energy, in our thermodynamic chapter many times, many different ways. And the most often used equation we know is delta G is equal to delta H minus T delta S. And we know G stands for Gibbs free energy, determining if a reaction is spontaneous in the forward direction. We know that if it's negative, it'll be spontaneous in the forward direction. If it's positive, by the time we're done calculating, it's non-spontaneous in the forward direction. You could think of that as saying it's spontaneous in the reverse direction. And if it came out to be exactly zero, you know that your system is in dynamic equilibrium. We know delta H has to do with enthalpy, the heat of reaction. Those terms are called exo and endothermic. Exothermic, we know, is the favorable, negative heat releasing variable. And if you see a positive delta H, you know that that is an endothermic process. S, of course, we know is entropy, the dispersal of energy, the random chaotic motion of molecules increases is the natural state. So entropy, we know, is favorable when it's positive. So I just took a snapshot of a quiz question, and it asked us to calculate delta G of reaction. And that little super knot up there represents its standard conditions. And the reaction is given below. We have gaseous carbon disulfide reacting with 3 molecules of gaseous chlorine, forming S2Cl2 and CCl4. So just any equation already balanced for us. The variables that we're given is delta H, and we're given delta S, and we're given the temperature. This reaction couldn't be any simpler. It really is just a matter of plug and chug to solve for delta G, providing every variable H, T, and S. The only trick is to remember to match units. So when we're asked to solve for delta G, calculate delta G, so I know that's my target. I know I'm going to set that equal to the delta H, which is negative 231.1. And notice that's in a kilojoule minus, and then we're given 25 Celsius, but we know that we need the Kelvin temperature. So we'll change that over, and that's always 298.15 at standard temperature. That's Kelvin. And then what I like to do with my entropy variable is remember to put this at negative 287.6. Oops. 287.6 over 1,000 to remind yourself that you have to match that unit and make sure that you're subtracting a kilojoule from a kilojoule. Now, I know that you can just slide the decimal as well, but this visually lets me remember I have to get the units alike. So just remind yourself, it's exothermic, negative H on the negative on the delta H for exothermic, and the entropy is actually negative. So that negative entropy means that it's becoming a more ordered system. And that makes sense. I can see I have 4 total gaseous moles on the left, recombining to a total of just 2 gaseous moles on the right. When 4 gaseous moles go on to produce fewer gaseous moles, the system becomes more ordered, and therefore entropy should be negative. So those signs are telling me exothermic and a more ordered system. All I have left to do now is grab my calculator. Please do the same with me and just double check we get the same answer. I'll take the delta G value, negative 231.1 minus, and I have 298.15 times 0.2876. That's me just sliding the decimal for the joules to a kilojoule for entropy. My screen reads 316.85. I should probably have just one decimal. And it'll come out to be a kilojoule per mole. Let me just pause and make sure. Let me turn the chat on. I haven't done that. If anyone has that answer as well, if you could just verify in the chat, or feel free to turn your microphone on. Yes, okay. Yay, we have a common answer. Beautiful. So I bring this one up because to me, this couldn't be any more focused on what the learning objectives are for this particular chapter. We're integrating the variables of enthalpy and entropy to solve for delta G. Again, the bread and butter. You will, guarantee you will see a problem like this one on your test. The next question I pulled is very similar, except instead of providing us delta S and delta H in the word problem, they make us work for them. Not that that's difficult, but it's just more steps to solve. Here's a reaction for the combustion of benzene. We have C6H6 in the liquid phase combusting with oxygen. Out comes carbon dioxide and water. Our formula is exactly the same, where we take delta G is equal to delta H minus T delta S. This is what we're trying to solve for. But now notice that they've given me data to solve for delta H, and they've given me data to solve for delta S. Instead of just telling me what they are, I have to do little, subtraction or addition and subtraction problems to figure out their overall value. Not difficult, but we wanted to review that. So I know it's going to be the sum of the products minus reactants. So I have the products, 12 carbon dioxides and 6 waters. And I'm putting them on this side because I know I'm going to be taking the products minus the reactants. And that's the same pattern for both delta H and delta S. And so the reactants here are 2 C6H6 and 15 oxygens. So to solve for delta H first, for no reason other than it's first in the data table, C6H6 is given to me as 49. Remember, there's 2 units in the balanced equation, so 2 times 49 plus 15 times 0, because we know that any element in its natural form, which molecular oxygen is the natural state of oxygen, it's assigned a 0, not only for delta H, but it would also be a 0 for delta G. So that's the oxygen part there. The next in the line there is carbon dioxide. We had 12 units of carbon dioxide, so 12 times negative 393.5 plus, and then there's the water, and we had 6 units of water, so 6 times negative 285.8. Sum of the products minus reactants. Let me take a moment, and that's not very neat. I apologize. I'm trying to write on the board and type. Let's hit this 12 times negative 393.5 plus 6 times negative 285.8. So simplifying the first bracket, that's the sum of the products. I'll do the reactants next. 2 times 49. and of course plus 0 for the 15 times 0. And finally, we're ready to say delta H is equal to negative 6436.8 minus that previous answer of 98. Delta H is coming out to be negative 6534.8 kilojoules for this part. Friends, we need to do the same process for delta S, just plus minus reactants, where we take the sum of each of those separate ingredients, just like we did for H. So here we have 12 units of carbon dioxide written first. That's 213.7. We have 6 waters. Minus, and up here for entropy of benzene, which we had 2 molecules of, it's 173.3. And of course, molecular oxygen in every compound will have a value for entropy, that's 205.1. Alrighty, and so our strategy then is to simply solve for delta S, and we'll be ready to plug in that formula, pulling out delta G. So let me have a moment with my calculator. Please hit with me. I implore you to practice.
I gotta put, I want to have enough pepper. You want to be seasoned.
I'm not finished. Would you please get out of my kitchen?
Okay, somebody's microphone is on. Can you please turn it off? Thank you. Awesome. All right, I have to start my calculation over. I got distracted. Hang on. 12 times 213.7 plus 6 times 67. I'll simplify the other side. And then do my subtraction just to show that we get a common answer there. I'm going to wait and see if we get the same thing, if someone would be willing to verify in the chat or turn on your mic. 3182.4 minus 3423.1. We've done is be able to solve the values to plug in for delta H and delta S to now go ahead and solve for delta G. So in the previous example, when we were working the same exact formula, we were provided delta H and delta S. How nice was that? But here, of course, it's the same process. We just have to do a little more work. We have to do the products minus reactants using the coefficients to solve for delta S and delta H. The last thing I needed to pull out again was looking at the temperature, 325 Kelvin. And then remember that 241 has to be put into the kilojoule unit, just to remind ourselves that we are always making sure to put our units as agreed units in the KJ form. And then, of course, negative 6534.8 is our delta H. Let's see what we find. Our Kelvin temperature is 325 times 0.241. And then negative 6534.8 minus that previous answer. A negative answer overall, meaning yes, this looks very spontaneous as a combustion would. this value makes sense to me. A combustion is very much a heat releasing reaction. Let me pause and see if you come up with a similar answer. See if I've made a calculation mistake anywhere along the line. Any questions? If someone would be willing to verify they found the same final answer, I would feel better. What might be a question someone would have if they stared at this question on the test, how to go about getting started? Any comments there about what might be a stumbling block for someone who looked at this problem? Just to debrief the strategy, we know that our formula, delta G equal delta H minus T delta S, we simply had to solve for the values of delta H, delta S, before we could provide the delta G. Oh, scroll down, I see that. Absolutely. Thank you. Is that far enough? Perfect.
Question.
Yes.
So how come you always just like change joules to kilojoules right at the end instead of just doing right from the beginning? And just, because I feel like leaving it until the end could just cause confusion.
So I guess I'm unsure
Like
where
right
you're
you have,
asking me to change it.
Like
Even just right up here?
yeah. I guess.
Oh,
I guess so.
My answer to that is it doesn't matter to when you do it. So if you redid this data table, 0.1733, 0.2051, 0.2137, 0.067, you would have all of them already in KJs, and you certainly can do that. I guess in my head, it's less math to just divide by 1,000 once instead of by 4 times. But it is really just what you prefer to do.
Okay.
Cool. Yeah, that's a good question. It's not right or wrong to do it one way or the other. It's just a preference at that point.
Gotcha. Thank you.
Yeah, of course. What else is on your mind? Anyone? Well, I'll go ahead and make a next slide and see what this brings to mind. Now, I had probably 3 or 4 students email me about these types of questions where we're asked to decide which reaction is either increasing in entropy or which reaction is decreasing in entropy. And I think the easiest way to strategize this type of problem is to think about the number of gaseous moles as reactants turn to products. As we understand that gases have the highest entropy, right? The complete chaotic motion to move in their container. Solids are the most organized, liquids are a little less organized, and of course, gases are the least organized. So, for instance, we're being asked to look through all of these reactions and decide which one does the system decrease in entropy. So think about that as becoming more organized as the reactants turn to products. For instance, in letter A, we have 2 gaseous moles of reactants. breaking down to form a total of 4 gaseous moles. And that's the key, is to only look at the gaseous moles as you make these decisions. 2 goes to 4. So of course we know the more molecules in the system, the more chaotic it would be. And so this one is actually going to increase in entropy. I was just reading your note there. What's in the little parentheses matters, doesn't it? Is it a gas? Is it a liquid? Is it a solid? Here in letter B, we have just 1 gaseous mole and form 2 gaseous moles. So that's more gas particles, therefore the entropy increases. Letter C, I have 2 gaseous moles recombining to form just 1 gaseous mole. Actually more organized, isn't it? This one I would label as becoming more organized. It's a decrease in entropy. Letter D, you see 0 gaseous moles forming 1 gaseous mole, so that's an increase. And letter E is kind of an interesting example. I don't have any gases, so I can't really rely on my trick of gaseous moles. I have a solid sodium hydroxide forming its aqueous ions in solution. So it's kind of just a dissolving process, isn't it? Just think of ordinary table salt. When you pour it into water and stir it up and it breaks apart and forms its electrolytes, you have 1 particle going on to form 2 particles. The process of making a solution. And so with that process, we know that that is more disorganized, and therefore that's an increase in entropy. So through all of those examples, we found just one where the system became more ordered. Now, with our letter C. Let me give you a moment of think time and see if this jogs a question before we go on.
I have a question, just not on the decrease or increase in entropy.
Okay.
You want me to like wait until everyone thinks, or just say it?
Is it related to entropy or just something totally random?
I mean, it's free energy change, so kind of random.
Let's wait on that. Yeah, let's wait on that and stay on topic, and then maybe I'll even hit your question in a next example.
Cool.
Don't forget though.
I won't.
Alrighty. So here's a next example, and I wanted to just kind of be quiet and let you look at this one. It's the same question as before, but just a different series of examples. I'm going to put 4 examples there. Which one of these is a decrease in entropy? I'd like to give you think time, and then in a minute or 2, we'll see if we get a common answer. How about this? When I say go, type the letter A, B, C, or D into your chat and just send it. And let's see what kind of responses we get if they agree. Go ahead and send your answer in chat. Beautiful. We all agree. Beautiful. Yes, yes, yes. I love it. So once you see one of these work, they end up to be quite easy. I agree. We had a half a mole of gas over here and none over here. So of course that's a more ordered system. Easy peasy. Good work, gang. Here's a new topic, trying to pull in as many different equations as we can. Here we're looking at thermodynamic data, and we're asked to solve for the value of K, the equilibrium constant. This type of question pulls in so many different formulas to apply them to pull out a value of K. I'm given thermodynamic value for delta H and delta S, and I'm asked to solve for K. So if we think about strategy, I know that ultimately delta G is equal to negative RT ln K, and that's what we're being asked to solve for. In order to find K, the equilibrium constant, we've got to know delta G, don't we? And I don't see that just yet, but I do know how to find it. Delta G is equal to delta H minus T delta S. So I've got to work a problem first to find delta G. Once you know it, I still have to do a little subtraction because they give me the individual components of the reactants and products. So with this particular example, we really do have quite a bit of a long pathway to ultimately get there. It's not difficult, it's just multiple steps. The other thing I just noticed is there's a typo. There's no oxygen anywhere in that formula. So NH4Cl is the final product. Okay, so let's do delta H, we know is product minus reactants. We know delta S will be the products minus reactants. We need to do a little bit of adding and subtracting there to figure out those two values. NH4Cl, the bottom one, so I'll do negative 314.4 minus the sum of NH3 and negative 92.3. I'll set delta S and then I'll grab my calculator just once. Here we have 94.6 is the NH4Cl minus the sum of the two reactants. There I go. Ran out of room. There we go. All right, so I'm going to grab my calculator. Let's see if I can. These were all coefficients of 1, right? So I'm good there. Negative 314.4. Yes. Negative 46.19. Negative 92.3. My screen, if I hit that right, negative 175.91. Here I have 94.6 minus 192.5 plus 186.69. And I'll do this right now. I'll just make that negative 0.28459 kJ. So I have that ready to plug in as a kilojoule. Delta T can be found by taking delta H, which we just determined here is an exothermic value of negative 175.91 minus 298 Kelvin times negative 0.284. That's plenty of decimals, I'm sure. 2845, 28459. Let me pause a moment and make sure we're in agreement so far before we do a next step. Agreement, anyone hit that and find the same thing? Yes, right. I love to be validated. Thank you. Now we're back to saying delta G is negative RT ln K. So remember, this was our ultimate question, was solving for that equilibrium constant. We just found delta G. And just to scroll back up again, notice, yeah, this question didn't give us the R. Sometimes it's provided, sometimes it's not. You need to remember that R is 8.31, and that's a joule per Kelvin mole. That's the ideal gas constant R. I have seen quiz questions where they provide that for you, but I've also seen quiz questions where it's not. And I do think it's on your equation page, the R constant written down in there, just in case you panic and don't remember it, it's on the equation page. But remember, here's the trick. If it's a trick, we have to make sure that our units match. So this negative 91.10 is a kilojoule is equal to negative 8.31 over 1,000 kilojoules. And then the temperature was 25 Celsius, so 298 Kelvin, LNK. So see what I've done, negative 91.10 is equal to negative 0.00831 times 298 Kelvin times the natural log of K. I want to make sure you see that the R constant and your delta G constant have to be in agreement as we're doing the math. Bring the R constant and the Kelvin temperature over. So just to see what I'm doing on my calculator, negative 91.10 over negative 0.00831 times 298. I'm just trying to isolate the natural log of K. And then let me pause and see if anyone else, I'm going to round a little bit, put a 9 there. Delta G over R times T is ln K. Just kind of showing our algebra steps to bring that over. Negative R T ln K. I'm just pausing and seeing if we're in agreement so far, and then we'll pull out K in just a moment, just letting you catch up a little bit. Sweet.
I have a question.
Go for it.
How did you isolate the LNK by itself? Because I had a problem doing that on the quiz. That's where I end up getting this question wrong.
I see. Okay, so we see that this is our formula, right? Delta G is negative RT ln K. These are all multipliers of each other. So if I want to isolate the natural log of K, this really is your put that in a parenthesis if that helps. My key sequence was right here. There's my delta G. And then in a parenthesis, I did divided by parenthesis R times T. But remember, you know, when we did our equation, it's negative RT ln K. So make sure you're making that negative sign down here. That's why I have a negative RT. So with your calculator, you would hit negative 91.1 divided by parenthesis 0.00831 times 298 close parenthesis equal. Yeah, that's my screen says 36.79, rounding a little bit. Does that feel more comfortable? We have one more step. That's actually to get rid of the ln, the natural log. So let me just rewrite where we were at. We had, oops, I changed that number somehow. Sitting top of your, oh, you got a different answer? I'm going to just verify this again. I'm going to hit negative 90.1. Oh, silly. You're ahead of me. Okay, my bad. Let me catch up. E raised to the 36.79 is K. Yes. And I see that in the chat. Somebody said this is what they got. I'm going to just round, and I'm going to put 5. I think we've matched. Perfect. So quite a few steps, wasn't it? I mean, talk about taking every equation we learned in the chapter and making it come out to play for this question. Again, not a hard question. You just had to go through a series of steps to find each variable you needed. So to repeat strategy, I'm just going to scroll up quickly for a moment. When we're asked to solve for the equilibrium constant, we know we need to know delta G. In order to know delta G, we had to solve for delta H and delta F first, pull out delta G next, then finally go into the K, the equilibrium constant. Let me scroll down again, just in case people were still looking at that. I'm just going to pause, wait to see if you have a question, and we'll look at another. Okay. With the problem we just worked, the equilibrium was at standard conditions. The standard conditions being 25 Celsius, each pressure would be at 1 atmosphere, each molar concentration would be 1 molar, all these standard states. Here's a problem that I did not work on Friday's review, but was requested, and so I pulled one out. It's going to be looking at the equation where we're looking at non-standard conditions. So let's take a read through. We're given an equation in which P2 plus 3 chlorines go on to form 2 PCl3s. All right, so here's our balanced equation. And the delta G standard conditions, and that's what you have to know is that little supernaut, this 0, superscript 0, stands for standard conditions. And as I mentioned, standard conditions are always 25 Celsius, 1 atmosphere pressure if it's in a gaseous form, 1 molar concentration if it's in solution form. And when we're looking at delta G is equal to negative RT ln K, this delta G is at standard conditions to meet the equilibrium constant. The delta G for this reaction is negative 642.9 kilojoules per mole. What is the value of delta G? And now, friends, notice there is no superscript 0. There's no standard state symbol there. So that's your clue to know that this is the non-standard value of delta G. No superscript there. So that value of delta G at 298 Kelvin for a reaction mixture consists of 1.5 atmospheres of the reactant P2, 1.6 atmospheres the reactant chlorine, and 0.65 atmospheres for PCl3. This was kind of at the very last of our lessons, the last few examples there in your note pack, where I talked about Q, which is called the reaction quotient, versus K, which is the equilibrium constant. And I have to tell you that our next unit, Module 3, is all about chemical equilibrium. You will be talking and learning about equilibrium constants, which are standard conditions, versus the reactant quotient, which is non-standard conditions. This is kind of intertwining this current unit on thermodynamics with a next chapter on equilibrium. So we get a little bit of mixture here at the end, seeding a little bit of the future chapter. The reaction quotient is solved the exact same way as the equilibrium constant, where we take the concentrations of the products over reactants and raise to the power the coefficients. They are stoichiometrically dependent, which is just fancy for saying we need to consider those coefficients when we write out the equilibrium expression. Q is the reaction quotient. It is found by taking, and these are pressures, so we're going to talk about partial pressures. The partial pressure of PCl3, because that's the product, remember that our goal is to always take products over reactants. Coefficients become the powers which raise each pressure to. Coefficient on the product is 2, so that value has to become squared. The partial pressure of PCl3 squared over the partial pressure of P2, and that's actually just to the first power, times the partial pressure of Cl2, and that has to be cubed, since that is a coefficient of 3 in the balanced equation. Q is an expression, just like the equilibrium constant at dynamic equilibrium, products over reactants, the coefficients become the products with which we raise. I'm going to plug in those numbers and solve for Q. The partial pressure of our product was 0.65, and that's squared over the partial pressure of P2, which is 1.5, and the partial pressure of chlorine was 1.6, and that has to be cubed. Let's solve for our reaction quotient, the ratio of products over reactants. Stoichiometrically dependent, 0.65 squared divided by 1.5 and 0.6 cubed. Let me round a little bit. Since we are at non-standard conditions, we solved for reaction quotient. This is the same process as the equilibrium constant if we were at standard conditions, taking products over reactants. Now it's a matter of just plugging into our formula right off the formula sheet. I just pulled that. It's my own handwriting from your formula sheet. We're solving for delta G at non-standard conditions. That equal to the standard condition of delta G, which was given to us in the problem. I have to go back and look. Negative 642.9. Plus RT ln Q. So plus 0.00831 kilojoules. Were we given 298? Yeah, 298 Kelvin. Negative 642.9 plus 0.00831 times 298 is 2.47638 ln(Q). Let's bring the negative 642.9 over to the left side, so it will become positive 642.9. Oh, wait. My bad. I need to put Q in. I'm not solving for Q. I know Q. 0.0688. Let me hit for us. I'm going to hit 0.00831 times 298 times the natural log of 0.0688. There. And then just simply take negative 642.9 minus that answer. That can all be done in one big calculator sweep, can it? I'm going to hit it again. 0.00831 times 298 times the natural log of 0.06688. Negative 642.9. Doing there. I don't hear many. Just waiting for you to have a common answer. Is that matching? Thing, Joe? Right here, if this is negative, this should be bigger, shouldn't it? I'm going to just check right here. If I hit this, negative 642.9 minus 6.628, it should be the bigger number. Anyone? Bingo that one. Yay. Yeah. All right. That's what I got the second time too. The reason I knew I messed up is I'm subtracting from a negative number, so the number should get more negative. Yes, perfect. We are in agreement, and that would end up to be a KJ.
So how come the positive coefficient just turned to a negative, like right there? You were adding negative 642.9 to 2.47, and then it just became negative?
Yeah, hit that out on your calculator. You go 2.47683 times the natural log of 0.0688. That's negative 6.62. So this term here of natural log, if you solve that, it's a negative number.
Gotcha.
Perfect.
Okay. It did come up on my calculator, so.
Sweet. Yeah. A lot to this one in the terms of we had to solve Q first. And once we solved Q, then it's just a matter of plugging in all those numbers to pull out delta G at non-standard conditions. And remembering that Q, the reaction quotient, taking the ratio of products over reactants, those values will be given to you. And just remember, coefficients become the powers with which you raise those values to in that expression. That was one that was asked for Friday, and I didn't have it prepared, so I wanted on purpose to make sure I got one in today.
So like what in the beginning of the problem, like what gave away that this was how you were supposed to solve it? Like just the atmosphere stuff or the pressure?
A couple of things to just denote there is, yes, absolutely, when they start giving us pressures, that we're going to have to start solving for a reaction quotient. And to me, the most obvious one was they gave me the delta G standard. Remember how we talked about that superscript of super zero there, standard conditions? But we're being asked to solve for a delta G that doesn't have a zero after it. And the only formula on your formula sheet for non-standard conditions is that guy right there.
Okay.
So to me, that was the bigger clue, is I'm asked to solve for a delta G without a circle after it.
Okay.
Let's look at this similar problem and just talk about how would you know the strategy. It's really very similar to what we just did. Let me give you a minute to look at this question and see if you can see word clues to know what reaction or what formula we're going to need. I know, yeah, you're right. Good. I see reaction quotient. I see that because I'm given some atmosphere data, just like we mentioned before. I'm also noticing that I'm being asked to solve for a delta G, but without a superscript zero. That means non-standard conditions. And so just mentioning the only formula we had was this guy, delta G standard plus RT ln Q. So just very quickly, we would know that the reactant quotient would be equal to the ammonia squared over the nitrogen times the hydrogen cubed. So that's looking at those pressure values where the stoichiometry becomes the power to which you raise. So I can solve for Q with the atmosphere data. The ammonia, 0.65 squared. The nitrogen is 1.9 atmospheres. the hydrogen was 1.6 cubed. So it's very similar to what we just worked. I mean, the identity of the molecules changed, but the math really is coming out the same. Let me see if I can pull out a Q. Oh, 543. And there's no units we'll learn on Q. There's no units on K. They're just numbers, and that's the magnitude of the number that's interesting. If it's a big number or a small number, we'll talk more about that in Module 3. Looking for this non-standard condition, delta G was given to me in standard conditions as negative 33.3. That's the R. The T is 298 Kelvin. And the natural log of our Q one big sweep on your calculator and you'll have solved for the non-standard value of Gibbs free energy. Thank you, Corey. This is me just giving you think time, see if something comes to your mind. Same, all right. Okay, so the last thing I wanted to talk about are some types of questions that ask you about when will a reaction be spontaneous and when will it not be spontaneous? At what temperature does it flip from being spontaneous to not? So I pulled out a question that asked me that very thing. At what temperature will a reaction be spontaneous? They give me a delta H, they give me a delta S, and I'm asked about a temperature for spontaneity. Remember, the only equation we know, the bread and butter of our chapter, is this right here. Our target variable is the temperature. Now, what we know is that when delta G is 0, we are at equilibrium. That is the temperature at the forward direction is exactly the same rate as the reverse direction. We want to know at what temperature it's not spontaneous, which would mean that it's spontaneous in the reverse direction. Here's our strategy. Let's solve for T when delta G is 0. That's going to tell me the exact temperature that the forward and reverse reaction is in equilibrium. Any temperature colder, that solved temperature will be non-spontaneous. And any temperature warmer which is another way of saying bigger than, would be spontaneous. Alrighty, so it's just kind of telling you the break point. We let delta G equal 0, plug in our delta H, which is an endothermic value of 62.4. The delta S is 301, so I'm going to just put that in as 0.301 kJ per Kelvin. Let's solve for T. So I'm going to bring the delta H over, subtract it. Negative 62.4 over negative 0.301 gives me T. So with all that done, you can say delta H over negative delta S is how you're pulling out T. It's just simplifying the algebra. And you realize that temperature will never come out negative. We just know there's no such thing as negative Kelvin temperature, right? There's absolute zero is nothing cooler than that. So I have negative 62.4 divided by negative 0.301. So I found maybe to 207.3. Perfect. And just in case they have Celsius, I'm going to put both down because I've seen the multiple choice where they give you Kelvin temperatures in the list, or they might give you Celsius temperatures in the list. But now all you would do to complete this problem is, okay, so when is it will be spontaneous? It's going to be any temperature that's warmer than 207.3 Kelvin or warmer than negative 65.7. If the question had said, when will it not be spontaneous, you would look for any temperature that's colder than that particular temperature. And if they asked, when is it at equilibrium, then of course it is that exact temperature. So put delta G in as 0, solve for that temperature, and then just look at that list in your multiple choice. If you want it to be spontaneous, you got to find something warmer. If you want it to be non-spontaneous, it's got to be something colder. That was the slides I had prepared. I'd open it up to say any other lingering questions. I know, Joe, I put you on pause for a moment. Did I hit anything that you might have wanted to ask about?
Yeah, that last equation, you actually hit it. But in that last question, you guys got negative 40.1, and every time I plug it into my calculator, I keep getting like negative 26.
So you think I hit something wrong?
I think I'm hitting something wrong.
Oh, well, thank you for being
I just
gracious.
don't know,
It's
like,
positive
how-
6.4. Negative point, whoops, negative 62.4 divided by,
I meant like the previous equation, like the last problem. That's where I kept getting the wrong answer.
this one.
Yeah, I plugged that
Oh.
in, just had it, and I just kept not getting that number.
Wow, thank you. If it's all right, I'm going to just back up and I'll re-hit this. I'll do the RTLNQ and make sure we have a common answer there. So 0.00831 times 298 times LN 0.0543. Negative 7.21-ish.
Once I'm just plugging in the last of it.
You bet.
Okay, I got it that time. I think what I did wrong was I didn't have a negative in front of the 0.0. I had a negative in front of the 0.0831, so it threw off my number.
Oh, you know what? I'm so glad you said that. And look carefully at your sheet, because when you're solving for delta G standard, it is negative RT ln K. It is. So that might be where you're confusing the two. But here,
Yeah.
notice that it is a little different, that it's now this equation. So that's a really good point. That negative RT ln K, we've been using that over and over and over. So maybe that carried in your mind.
Okay, yeah, no, that's definitely what happened.
Okay. Well, I'm glad that you figured it out. Perfect. And then just any other opportunities to ask questions. Oops. So was this spontaneous? Are you looking with this spontaneous at this temperature? To be spontaneous in the forward direction, you have to look at the list of choices in the multiple choice, and there'll be just one correct answer. It's not like you have many to choose from. There's one correct answer, and it will be the answer that is warmer than 207 Kelvin or warmer than negative 65 point Celsius. So once you solve for the temperature, you've got to look at the list and decide which one of those meets the criteria. Because when you said, is this spontaneous? Right now, at this particular temperature, my answer would be no, because the forward is at the same rate as the reverse. That's what equilibrium is. So we got to push it to be warmer to favor the forward direction. You got to cool it down below that to favor the reverse direction. So, you know, that's a really good point. I've not seen this in the standard bank, but this typically will not be a multiple choice in the bank. It's not going to say 207.3, and then we'd get so excited because our calculator matches an answer, and so you circle that answer. You want to look for spontaneity. It has to be bigger than that number, warmer. Good. You're welcome. Anyone else? Thoughts today? Who was for tonight? There's a game tonight. Did you know that?
Super Bowl, yeah.
Okay, I have a quick question.
Yeah.
There was a question on the quiz about, like, it was like the questions like with the target equation, and we had to find the free energy, and it would be two, like.
Could this be something that you might be thinking of?
Yes. Yeah.
Oh,
exactly.
Look at that. I'm so well prepared. What total luck, trust me. This is an application really of Hess's law that we did last chapter. And now we're just using delta G's instead of delta H's. So I always think of these as just like little puzzle pieces that I got to put these two pieces together, reaction 1 and reaction 2, to somehow build the target. And then whatever you do to those elementary reactions, you have to do the same thing to the delta G. So this is just my out loud thinking. There's so many correct ways to think. This is just me thinking out loud. I bring my eyes to the first reactant in the target equation for no other reason than it's written first. I then go into the elementary reactions and try to find where it's located. Alrighty. So where do we see sulfur dioxide? Well, I see it here. And the nice thing is it's the only place I see it. So what information does that tell us about the first reaction? Like many we have, but it's on the wrong side of the arrow, huh? So I think we're going to have to reverse that direction. When we do so, we flip the sign of the delta G. So if I rewrite SO2 pointing at X plus O2, its delta G is now positive 300.1 kJs. The oxygens, I don't think are very helpful for me because they're located in both of the elementary reactions. So I just tend to skip it. I don't really need to worry about that. But I do like looking at the SO3 because it's unique to this spot here. It's the only place I find it. I like the side of the arrow it's on, the product side, but I have 2 and I only need 1. So what that's going to tell me is to cut that reaction in half. When I do that, I'll cut that value in half. So I would have S plus 3 halves O2 forming SO3, and the delta G is now negative 742.1 halved. And when I add those two equations together, the sulfurs cancel. 1 mole of oxygen and 3 half moles of oxygen. Think of this as being like 2 over 2. It's 1 oxygen. 3 halves minus 2 halves is 1 half. Sulfur dioxide, half an oxygen, pointing at SO3. We just add those two together. So my first one, 300.1, as a positive, reverse the direction, plus negative 742.1 over 2, cut that in half, and I think that's 70.95 negative value. Did I hit your question with a good example?
Yes, thank you. I see where I messed up. It was a simple math mistake. Thank you.
Darn it, right? Yeah. That gets me too. So I'm calculating along and I feel so confident and I go, oh, I don't see an answer. It's usually my human error with me and my calculator. One last piece of advice as you're getting ready to celebrate your learning. Remember that there are 5 review questions from Module 1, 5 integrated, I call it distributive practice, where I bring in some last chapter sprinkled into the new chapter. So questions about like specific heat, those types of things could be on there as well. Any last comments, questions for the group? I'll hang out until everyone is gone. I wish you luck on your test. Enjoy your game tonight. Oh, go back to the previous question. Sure. You're welcome. Yep, so I'll just hang out till everyone's gone. Feel free to hang out if you have further questions.
Hey, Professor, sorry if you hear background noise. I'm at work right now.
Oh, yeah.
But on the second attempt, or like on my second attempt for the quiz, my question number 6, the value of delta G at 141 degrees Celsius for the formation of phosphorus trichloride. I was wondering if you could just go over that real quick, please.
Yes,
It deals
I have
with
that
like
question.
finding delta G.
Okay. So
at a different temperature.
a moment of patience because I'm going to have to pull it up. Alrighty, I don't have that.
Thank you so much.
Oh yeah, I'll be just a.
That question popped up twice on the quiz too.
I also had a whole bunch of questions that came up the same.
Yeah, like the exact same one. Yeah.
You know, all right, thank you for telling me that, because what that means is that a question is appearing in the test bank multiple times. Does that make sense? Um,
Oh, well, I didn't know how to solve it twice,
So-
so.
right, and that's not fair. Or you're like, yay, I got that twice.
Yeah.
So if you happen to, if you don't mind, whenever that happens, if you could just send me a note about which problem it is, because that would let me go in and delete one from the test bank. Because if it's duplicated, it's randomly pulling different questions. It just happens to be in the bank twice. And
Gotcha.
since there's like 100 questions in the bank, it's really difficult for me to find which ones are duplicated. But if you have that problem, it would be so helpful to know which question it is so I can eliminate one of them. But
Gotcha. Definitely will.
yeah. Was it a hard question? Or is no?
I mean, it probably is hard, but we just need the explanation.
Okay. So this is Ryan Locke. Is it that? No. Okay, they're fast. Thank you for your patience. I'm trying to get quiz 2, attempt 2, Ryan. Number 6, you say? 5, 6. Oh.
It was
So,
the calcium chloride one, yeah.
oh, so that's not this one. Calcium.
The value of delta G at 100 for the formation of calcium chloride.
Are you looking at the question or no?
Yeah, I'm looking at the question. I wrote it down because I didn't know that one. That was the same one that he asked.
It must not be your second quiz. Did you tell me quiz 2? Maybe it's.
If you can't find it, you can look on mine too. 'Cause mine was on the second attempt as well.
So I have Ryan pulled up. Ryan, can you tell me what attempt I should look at? Do you know, Ryan? Okay.
He said he was at work, so maybe he just can't talk.
Sorry, I'm at work, so I'm trying to text in chat as well.
Okay, no worries. Yeah. Oh, stuff in the chat block track. Second attempt. I don't see it in the second attempt. So, Joe, let me pull up your quiz. It's the same question.
Yep.
Your second attempt as well.
Yeah.
And it's number.
It should be number 6.
Gotcha. That I found it there.
Cool.
So I'm going to just make a new slide and write down some data. Okay. Whoops. Here's an equation that gives us calcium as a solid reacting with gaseous chlorine, and it's pointing at calcium chloride. And that is a solid phase. Perfect. And it says, tell me the delta G at 100 degrees Celsius. At 25 degrees Celsius. Delta H. Delta S. And I'm just trying to make sure I don't make a mistake. I think I have that. So this is what we're being asked to solve for. Delta G, 100 degrees for the formation of this from its elements. At 25 degrees, these are the delta H. So when we solve for delta G, we're going to pull out negative 795.8 minus 373. That's the Kelvin. And then negative 0.1598. Does that look like what you solved?
Yeah.
And if both got it wrong, it makes me wonder about the question. So negative 795.8 minus 373 times negative 0.1598. My screen reads negative 736.19, so I'll just round. Anyone else get that? Same, okay. And that is an option actually in the answer list. And Joe, I hate to call you out, but can you share the answer you picked? And I'm just curious if I could understand maybe how you got there, and maybe we could find the algebra mistake.
I think where I just got my biggest confusion, and I know it now, is just seeing those two different temperature readings threw me way off. And I was like, 25 and 100, like, which one am I solving for? But now looking back on it, I'm like, that just means standard conditions. Yeah, right?
That's okay. Awesome.
Okay.
Yeah, that's an aha moment. Because you're right. You do see two temps in there. All
Yeah.
that 25 degrees is telling you is that those are standard values that we stamp on the chart. You're
Okay.
right. But
Wasn't
it's
able to make
not
it
the
to that
temp you
Friday.
use. Oh, yeah, no worries. Just so we have an aha moment today, we're good.
Cool. That makes me feel better, so thank you.
Good. Yeah, you're welcome, Brian. I see in the chat something about a combustion. I'm trying to scroll back up. So I'm trying to decide what you might mean about a combustion question. When I started, I thought with a combustion question here. This is a combustion question.
You did, and I was able to, because that was the one I had. So I was able to realize that my order of doing the question was a little bit funky.
Oh, so you're good now with the combustion? The other topics?
Hey, Professor, I have one more question. This was on my third attempt, question 10. What is the equilibrium constant for the reaction below 25 degrees Celsius? I was wondering if you could kind of walk through that, please.
Okay, I'm going to look at question.
Also, this is Brian Lotz.
Okay, thanks, Brian.
And once again, thank you.
Oh, yeah. So I'm just going to make a clean screen, and I'm going to write down the problem as I see it. I have to turn my screen a little bit so I can read this. We have magnesium carbonate in equilibrium with MgO and carbon dioxide. What is the equilibrium constant for the reaction below at 25 degrees Celsius? So I'm just kind of recording some data that's in the question. They give me the delta G of formation of magnesium carbonate. that value is given as negative 1028.2. They give me the delta G of formation of magnesium oxide as negative 568. Moment of dyslexia there. And delta G of formation of carbon dioxide is given to us as 94.4. Okay, and these are all KJs. So what's interesting here is our formula, we know that relates delta G and K is this one, negative RT ln K. The delta G has to be of the reaction at standard conditions. So what we'll end up doing is saying we've got to find the delta G of the reaction by saying we just have to take the sum of the products minus the reactants. And that delta G will go into our formula to pull out K. So the MgO value, magnesium oxide, is the first product, negative 568.8, plus the other product, which is carbon dioxide, is the sum of the products minus the reactant, which was your magnesium carbonate, and its value is negative 1028.2. So the delta G in the standard form. So let me hit that with that and see what we get. We have the sum of the product minus reactants, negative 6.8 plus negative 393.4 minus negative 102.2. Oh, a positive 66. But I'm going to pause and see if someone can verify that. I'll hit it twice just to be sure. And then minus negative 1028.2. Twice. Anyone else? I'll assume it's good. No one's yelling at me. If I make an error, you'll turn your mic on. Well, now that we have the delta G part, that's the 66. That's negative 0.00831 is the R constant, times the temperature, which they told us 25. Yeah, that's 298 Kelvin. And then times ln K. Negative RT ln K. 66 divided by negative 0.00831 times 298. You got 65, I got 66. Darn it. Okay, we're close. Negative 568.8 plus negative 394.4 minus negative I got 65. Dang it. So that was to my rescue here. Thank you so much. Perfect. Okay. All right. Small repair, but nonetheless, let's put in that 65. And then I'm going to divide by negative 0.00831 times 298. E raised to the negative 26.25 is K. So drum roll, please. Let's see. We met the answer on the quiz. It's always a good feeling. So 4 is what they rounded it to, 4 times 10 to the negative 12. But that was kind of the strategy there is just having to go through and find the delta G using products minus reactants. Products minus reactants got us the delta G of the reaction. When I subtracted correctly, I brought 65 down, divided by R and T, and pulled out K from that. Sweet, someone second my motion. Yeah, and I have to tell you, I cheated and looked at the answer key and we matched. That's always a good feeling. Good question there. So I wonder if you're looking at the delta G's and well, which one do I use to go on? It's probably a good hint to know that you're going to have to do some subtracting there, products minus reactants. Oh, we did some good work.
Yeah.
Feeling more confident, I hope. We've been at it an hour and a half. Can you believe it? Time flies when you're doing chemistry. So crack myself up. I wish you all the luck. Don't forget to do your test earlier rather than later to allow yourself some downtime this evening. Maybe even have some chicken wings. Is that on your menu for Super Bowl Sunday?
Already ordered
It's
up.
not on mine. Did you? All right. All right. All right, friends. Well, good luck. You did some really good work. I'm sure it will pay off. And I'm just an email away if you have questions, okay? Proud of you.
Cool. Thank you.
Yep. Yum. All right. Yeah. Have a good evening.
Thank you. Have a good evening.
Thank you.